right? So the other day we were discussing about few things. I'll just quickly summarize them and then we can go ahead, right? So see, so first thing we learned was about Raoult's law. Raoult's law, where we learn the total pressure of two binary solutions, where both of them being volatile is P naught A XA plus P naught B XB. And partial pressure of A can also be, represented in terms of Raoult's law this way, and P total into YA as per Dalton's law. We also learned that 1 by Pt is equal to Ya by P naught A plus Yb by P naught B. This is another way of representation. We learned that in a graph we can represent a total pressure line in this format. This is the total pressure line in terms of mole fractions of Pt as a function of Xa and Xb, while this way if we write it is P total as a function of Ya and Yb. Okay. We also learned the fact that when you have uh, you know one particular mole fraction identified for an element, for a component here, let's say I will take this particular component here, which is, let's say, Xa here, correct? And in this graph somewhere here, if it goes this way, as it touches here, this represents Ya, which is the uh, liquid composition, liquid mole fraction for a particular component, and this is vapor mole fraction for a particular component. Okay, this is one important area which we learned. So please do understand that carefully. So this particular graph is what we call it as VLE, vapor liquid equilibrium. Then we also learned there are ideal and positive and negative deviation solutions. That is positive deviation from Raoult's law, negative deviation from Raoult's law, ideal solution as in which follows Raoult's law. So the one which follows Raoult's law, there we learned that AB interaction is same as AA interaction is same as BB interactions. While for positive deviation, we learned that AB interactions will be less than AA interaction or BB interaction. While for negative deviation, we learned that AB interaction is greater than AA interaction or BB interaction. We learned that delta H of mixing for this is 0. Delta H of mixing for positive, it is greater than 0. Delta H of mixing for negative deviation, it is less than 0. Delta V of mixing is equal to 0. Delta V of mixing is greater than 0. Delta V of mixing is less than 0. Delta S of mixing is always greater than 0 in all the cases. Same and same. That is not going to change. Delta G of the mixing will also remain less than 0 as long as it is mixing properly. So it is miscible, which we call it as miscible liquids. As long as they are miscible, delta G will always remain negative. Got it? I gave you a bunch of examples for ideal solutions, positive deviation, negative deviation. Got it? These are few important areas which we need to which we have discussed, and make sure that you revise them thoroughly. Now, coming to the next topic, we learned about uh, colligative properties. Colligative properties. So in colligative properties, I specifically mentioned four types. relative lowering of vapor pressure, and elevation in boiling point, and depression in freezing point, depression in freezing point, and lastly, osmotic pressure. Okay, when it comes to elevation in boiling point here, okay, we learned that first we need to add a non-volatile volatile solute. For non-volatile solute, which is B, as you add, right, then we know that PA, P naught A minus PA upon P naught A will come out to be mole fraction of B. Okay, mole fraction of B can be written as number of moles of B by number of moles of A plus number of moles of B. This particular term is what we call it as relative lowering of vapor pressure. Okay, which suggests that, as the number of moles of B increases, delta P value increases. Correct? So what happens in that case? See, because the vaporization is happening to be lesser here, correct? So you would notice vapor pressure of solution decreases because this factor is of solution. So I'll just write down this as P solution, P of solution. So P of solution decreases. Next, we learned about elevation in the boiling point. Okay. For that, I ask you to recall how the Clausius-Clapeyrion's equation work. That is pressure versus temperature, wherein ln P, right, will be equal to delta H of vaporization by RT square with minus plus delta S by R. Okay. Sorry, this won't be there. This term won't be there, as I keep it as a differential form like this. Got it? So now if at all I plot that P versus T here, so you would get an equation like this. So which means if you're operating at a particular standard pressure, that is, if the pressure is 1 atm, then the temperature value what you will get is what we call it as the boiling point. That reminds the point that boiling point of a liquid is a certain point when vapor pressure of that liquid will be equal to pressure of atmospheric pressure. So when that happens, we say boiling has been happening. Okay. If I go back and get this graph here, the VLE graph here, got it? Then you will realize that this particular point, right? This particular point where, you see the mole fraction. This is the vapor pressure of the liquid. And if this liquid vapor pressure matches with the atmospheric pressure, then this point will become this point of composition is at boiling point composition. This will be at boiling point composition. Okay. Now, using various derivations, we derived something the other day, that delta TB, that is how much amount of boiling point, extra boiling point temperature that has to be raised in to get back to that 1 atm is Kb into molality of the solution. Molality of the solution. This is what we learned. Okay. I hope you guys remember this. Got it? So now this becomes a very important method also to figure out something which is unknown. Let me tell you what exactly I meant. You know that Kb also we found out that it is a constant value which is equal to RTB square into molar mass of the solute. Okay, sorry, molar mass of the solvent, that divided by 1000 times of delta H of vaporization. While we came across the derivation, we learned that these are all the constants which can be represented as KB. Yeah. Now notice this something here. Suppose if at all I have some unknown non-volatile solute with me. Okay, imagine some kind of a stone, which during maybe a meteor shower or something, during some cosmic landing, something like that. There is some kind of a stone or some space material that has, crashed on Earth. And imagine if that stone has some composition of elements, and you want to find out what is the molar mass of it. So we can do that quite easily. Here you can see abelioscopic is a one good method by which you can do it. Okay. So abelioscopic method implies that you use the boiling point temperature and see how much difference is the boiling point that you're getting on adding certain component of the unknown solute. Okay, that is delta TB will be equal to KB into molality, that we know. And can I write this as KB into molality as weight of solute on molar mass of solute into weight of solvent in kgs. So if at all I write it in grams, I need to multiply 1000. This time this will turn into grams. Okay. Now bring this back onto the left hand side. So ms, which is the weight of the solute, unknown element. So that will be equal to kb into ws into 1000 divided by the delta tb into weight of solvent in grams. So this way we will be able to figure out what is the molar mass of the solute. Clear, everybody? So whenever we want to know what is the unknown molar mass, so this is one easy way out. Okay. So now we can actually figure out what is the unknown molar mass. Now, why this is relatively better than freezing point method, correct? For identification of the vapor pressure or unknown molar mass here. That's what we will discuss. Going ahead, we'll discuss that. So for now, remember that this is the formula that you can employ for finding out the molar mass of an unknown solute. Got it? Now let's dig some detailing about depression in freezing point. When we plot vapor pressure versus temperature using Clausius-Clapeyrion's equation, we learned that this is how the graph goes. And of course, this is the way it will keep moving across various temperatures. Now, this is for solvent. Now, if I add some solute to it, then for solution, this is how the graph goes. If I add more concentrated or more concentration of the solute, then the graph goes like this. Okay. So there was a pattern that has been noticed while you plot the experimental data here. The pattern is like this. Suppose for a solvent, if the graph is going like this, correct? There is a certain point after which suddenly it starts falling drastically. So the vapor pressure value drastically drops here, correct? Like this. Now, this could probably happen when the state of the component, state of the solvent is changing, which means up to this point, it is majorly in liquid state. And from a point onwards, it started to freeze. From this point onwards, it is starting to freeze. Got it? So that means when the freezing point comes into the picture, this is how the graph would vary. Okay. Now notice this one. If I take this as the 1 ATM line here, correct? If at all I take this as the 1 ATM line, okay? So, of course, if you have gone back to the questions here, I plotted this way that somewhere here we had 1 ATM line, isn't it? This way, okay? Now, suddenly you might wonder, sir, how come 1 ATM line is coming here? Got it? So, my point is, as you start doing it for solvent here, if you go somewhere at this point at 1 atm, you will know that you will find here as boiling point. You find this as boiling point. But if you're drawing with respect, because for we don't have any other equation, just like Clausius-Clapeyron's equation, we don't have any other equation where a solid state of a solute or solvent is being represented in a formula. Okay, but what you would notice is that at this point the graph would go something like this. Actually, it will go like this. Okay, and then it will come down, so basically this is how you need to check. So here you will notice this has 1 atm. This is still 1 atm. I mean, at 1 atm, this you will notice as boiling point, this you will notice as freezing point. So this is how usually it goes, correct? Vapor pressure will go. So that's why I am only extrapolating that graph and showing it here. So don't get confused that, sir, how come 180 is here and suddenly at lower point also we have 180. Okay. And you know that when it comes to vapor pressure of a solid, because now you have a freezing done here, correct? When you have freezing done, which means you are expecting there will be large quantity of something like ice and a very small quantity of liquid water on top, okay, or liquid water at the bottom, wherever, based on density, correct? At that particular point of time, if you keep the vapor, if you identify the vapor pressure, now we'll say, sir, solid का कौन सा vapor pressure होगा या liquid का हो सकता है, solid का कैसा होगा? See, solid vapor pressure is about converting the substance into different state, which means its tendency to convert solid to liquid is also called as vapor pressure. The tendency is also called as vapor pressure, everybody. It doesn't have to be the precise vapor zone only always. Okay. Let me explain in a simple terms. Okay. Don't get confused. Please check. See, let's go point by point. So when it comes to freezing point, these are the graphs that you will notice. The first graph represents this was only for solvent. As you go to the solution, the same type of graph now changes after it reaches the point B, which means if this was the freezing point for a pure solvent, now after adding some solute, the freezing point actually decreased. That's why if you notice, salt water, correct? Pure water freezes at 0 degrees, but salt water freezes at -5, -10 and beyond. Got it? So it will keep on going down. So if you may have noticed the water coming from Himalayas all the way towards Ganga and from Haridwar, if you see from Rishikesh and Haridwar, as the water keeps coming from Ganga, correct? Because it has large number of dissolved minerals and salts in it. Okay, you will see water is actually flowing at -20, -10 degrees, correct? But yet it is in liquid state. Why? Because they have so much mixed salts in it, their freezing point is quite low. It is around -40, -50 degrees is their freezing point. So you could imagine when a solute is added to water, correct? The freezing point drastically goes down depending upon how much quantity you are adding. Okay. So now have you noticed the similar logic what we have earlier applied for uh, you know boiling point? See here, can you see A, E, sorry, A, D, and B versus that versus A, E, and C, correct? So now if you notice that uh, BD is the difference in the freezing point, correct? So delta TF1, correct? And difference of the vapor pressure, how much you got? This one, AD, is proportional to vapor pressure 1, isn't it? And sorry, difference in the vapor pressure, delta P of 1, and delta F freezing point 2 is directly proportional to delta P of 2. So that implies Delta P is also directly proportional to delta TF. Just like how we identified that relative lowering of vapor pressure was proportional to change in difference in the boiling point temperature earlier. Going back to this graph, see, this is what I'm trying to tell. So this is the same thing we discussed, that change in the vapor pressure is directly proportional to change in the boiling point. Same way I'm doing it for the freezing point also. So now you could relate that the same kind of a graph can be related here as well. Got it? Now, what is this one? So delta TF is proportional to delta TF is directly proportional to delta P by P naught. Okay, which is nothing but relative lowering of vapor pressure. And we can relate this as delta F is equal to some constant A into mole fraction of the solute. Correct? If you remember, the same type of derivation which we have done can be done here also. Okay, just a minute, somebody's at the door. Right. See, delta TF is equal to A into mole fraction of the solute. Using the same concept as that of elevation in boiling point, we can derive very similar things here. That is, Kf will be equal to R TF square into molar mass of the solvent upon 1000 into delta H of fusion. Earlier it was vaporization, now it will be fusion. That's it. And delta TF will be equal to molality into Kf. So just like how you get the formula for elevation in boiling point, you will get a very similar formula for depression in freezing point, everybody. Okay, right? Just like how we call Kb as the ebullioscopic constant, here Kf, okay, Kf is termed as cryoscopic constant. Cryoscopic constant. Cryoscopic constant or depression constant. Depression constant or freezing point constant. These are all very similar terms how we use it in boiling point. Okay. Now, I hope you got an idea that how the similar derivation can be applied to get this formula. Honestly, these derivations are not there for your syllabus. You just need to learn the formula and learn to apply that correctly. Okay. Now notice, I was telling you something about vapor pressure. Now, theoretically, this understanding has to be very clear to you. Okay. So let's focus more on that. For that, what I'll do, I'll take an example of H2O. Okay, let me take this example. For example, when I say H2O solid, which is ice, okay, it is in equilibrium with H2O liquid, which is water, correct? These two are in equilibrium, correct? Then this equilibrium exists at 1 atm external pressure. 1 atm external pressure, correct? 1 atm external pressure. Now, my question is, when 1 atm external pressure is present, then what is the vapor pressure here? Because when I use the terminology for boiling point, there it was pretty clear that the vapor pressure of the liquid has to reach 1 atm so that the boiling begins. And that particular temperature is called as boiling point temperature. So for that, it's pretty clear. But how do we define freezing point in a very similar term? Now, what freezing point here means? It is the tendency, everybody. That is tendency of, first C, tendency of H2O solid to convert into H2O liquid. This is called the vapor pressure of ice. This tendency is what we uh, this tendency is what we describe as vapor pressure of the ice. Okay, similarly, tendency of H2O liquid to convert into H2O solid, which is ice. That is called the vapor pressure of water. Vapor pressure of water. Got it? So this is not in literal sense that this vapor pressure मतलब ऊपर vapors होना चाहिए वो pressure apply करना चाहिए. It's not in that sense. It is always in terms of tendencies we are discussing. Okay. So basically at equilibrium, what is expected? That is at equilibrium, we are expecting that the vapor pressure of ice must be equal to vapor pressure of water. That means the tendency to convert in both sides should be same. Then we say equilibrium has reached. At equilibrium temperature, the temperature at which this equilibrium attains is called as the freezing point temperature. Correct? This is what is the actual definition. Clear, everybody? Now, what would happen when you add some solute to the solvent? Now, that's the interesting part. Okay. So imagine like this. Suppose if you have liquid here, pure water here, and in pure water, you added some kind of a sugar. Okay. You added some sugar to it. It got some sweet flavor. Correct? And the water is at a very low temperature. It started to freeze now. So now there are two things we can identify here. One, you need to check out H2O solid. When will it reach the equilibrium towards H2O liquid? Correct. But now this is for pure solvent. For pure solvent, this is what you will search. But for solution, what you will search, for solution, you will search like this. H2O solid, it is in equilibrium with, you know, solution in liquid. Solution in liquid. This is for sugar solution. This is for sugar solution, everybody. Got it? Now, what is the difference between these two? Check out carefully. Suppose, listen, everybody, if the vapor pressure tendency, that is the tendency of solid to convert into liquid here, let's say its tendency is some x units here. X unit, whatever units maybe, it could be in ATM or it could be in pressure, force, anything. Okay. Similarly, the tendency to go on this direction will be y. Okay, this direction will be y. Correct. This is for pure solvent. Now, what would happen for a liquid solution now? If you have solution, now problem what it is for ice to convert into liquid, it still will have the same vapor pressure, but for solution to convert into solid, now it will have a different vapor pressure, and you will notice that Z will be less than Y. Now let's think logically, everybody. Okay, I'm sure everybody is aware of ice popsicles. Okay, or chuski. I'm sure you all have come across that, or you already ate that once, or once in your life. Correct. Now, when it comes to ice popsicles, right, you'll see that there is a sugar flavor or some kind of colored flavor that has been added onto the ice. Correct. Now, tell me about it. when one of the reasons why we use that is we just try to suck out all the sugar out of it, isn't it? So when you suck out all the sugar out of it, you will notice that leftover is only pure ice, correct? Now that ice does not have any dissolved sugar in it. Think about it carefully. That ice will not have dissolved sugar. That means solution is not freezing, only solvent is freezing. But when it is in liquid state, there is not only one solvent, there is always a solution present in it. Just think about it for a minute, everybody. Okay. So basically जब फ्रीज होगा, सॉल्यूशन फ्रीज होगा तो सिर्फ आइस फ्रीज होता है, उसके साथ में जो सोल्यूट है वो फ्रीज नहीं होता है. I'm guessing this logic is clear to everyone. Yeah. Okay. So thank you. So when it comes to uh, solution, everybody 2 मिनट आराम से सोचिएगा सब लोग. ओके. सो इफ यू हैव सॉल्यूशन ना बेटा, सॉल्यूशन को फ्रीज करो, सो इट विल कन्वर्ट इनटू आइस, बट वो आइस में सोल्यूट पार्टिकल्स नहीं होते हैं. बट आप ऐसे नोटिस करो, जब आइस मेल्ट होता है तो वो जो पार्टिकल्स है वो सॉल्यूशन में घुल मिल जाते हैं. दे आर मिसेबल देयर, करेक्ट? And this is the nature of the solution, everybody. Okay. That's why that is the tendency to convert ice to solvent, or ice to liquid solvent, or ice to liquid solution is same. This is the one. ये दोनों same रहेंगे. But when you go backwards, right, the liquid solvent converting into solid solvent, उसका मैग्नीट्यूड जो भी रहेगा, दैट विल बी हायर कंपेयर टू दैट ऑफ सॉल्यूशन ट्राइंग टू कन्वर्ट इनटू आइस. वेरी सिंपल रीजन, सॉल्यूशन को आइस में कन्वर्ट करने के लिए थोड़ा ज्यादा अमाउंट ऑफ एनर्जी स्पिल करना पड़ेगा. क्यों? बिकॉज नाउ द पार्टिकल्स आर इन बिटवीन. सॉल्वेंट पार्टिकल्स सारे एक जगह इकट्ठा करने के लिए सोल्यूट पार्टिकल्स को सेपरेट करना पड़ेगा. सो इफ यू वांट टू रिमूव दोस सोल्यूट पार्टिकल्स, यू रिक्वायर मोर एनर्जी टू डू दैट. That's why you need to go to further lower temperature if you have to freeze it. Okay. So now you can see x is equal to y when it is at freezing point. Now you notice x is not equal to z, because now the z value is lesser. So if you want to make these two values equal, you have to go and take it to further lower temperature, everybody. Only when you take it to further lower temperature, then both their tendencies will match and it will start freezing. I suppose this logic is clear, everyone. Ayushi, did you understand what I said, bacha?
Yeah, sir.
Very good. Pratisha,
Yes, sir.
Diksha, Tanish.
Yes, sir.
Good. Okay, I'm assuming all of you got this point. Chalo. So this is about how the depression freezing point works. Okay. I'll show you all the application with questions. Don't worry. Okay. As of now, understand the theory carefully. Right. Now, let's see about the fourth colligative property, which is osmotic pressure. Okay. When it comes to osmotic pressure, look into it. To figure out osmotic pressure, we require two, uh, two liquids. One side, we should have only solvent, and other side, we should have only solution. Both of them should be only separated by semi-permeable membrane. Okay. Semi-permeable membrane usually is made up of various cellulose, okay, parchment papers, correct? So those kind of material. So semi-permeable membrane should be present between these two liquids. Now what would happen? See, listen up. Can I say something that across the solution side, solution will apply some amount of vapor pressure on it. Let's call it as P solution. And the solvent side, it will apply some amount of vapor pressure, which we call it as P naught. Okay. And you know that P naught is always greater than P of the solution, isn't it? So in such case, correct, can we say that now the pressure on this side is more as compared to that of pressure here. And because the pressure is more, and you know that semi-permeable membrane will only allow solvent particles to move. It will not allow solute particles to move through its filters. In such case, we can expect, because the pressure is more here, the liquid will start to move from solvent towards solution. Got it? It will start moving from solvent towards solution. Okay. So this difference in pressure, correct? This difference in pressure, which is creating a kind of movement of solvent particles here, is what we call it as the osmotic pressure. Okay. So due to pressure difference between solvent and solute, the solvent molecules will move towards solution. And this phenomena is called as osmosis. Clear, everybody? And the difference in the pressure is what we call it as the osmotic pressure. See, osmosis is a phenomena where movement of low concentration, I mean particles from low concentration are moving towards high concentration. And that's what is happening. Solvent is at low concentration here or zero concentration. Here solution is at high concentration and solvent particles are moving. This is called uh, osmotic pressure. Here. Now what is the formula you will apply here? See, osmotic pressure pi is the term used for osmotic pressure. That is proportional to difference of the pressure, correct? Okay, so that is equal to, sorry, this is equal to difference of the pressure. And this difference of the pressure is directly proportional to concentration, because more the concentration, more is the amount of pressure. And it is directly proportional to temperature, because if there is more temperature, faster will be the movement of the solvent particles here. So keeping that into mind, so pi is directly proportional to concentration and temperature. Concentration and temperature. So if I remove the proportionality, I will get a constant here, which we read it as CRT. R is very similar to that of a gas constant. Okay. So this is now like a similar to gas constant with almost the same value you will get. So the value will be 0.0821 atm liter per mole per Kelvin. These are the units. Okay. So therefore, it implies pi is equal to number of moles of solute upon weight of, sorry, volume of solution in liters into R into T. This is how you define the pi value. Right, everybody? Okay. So you can see again pi is dependent on number of moles of solute. So the whole idea that pi is I mean, the colligative property is a part where it depends on number of moles. That's what we are trying to prove in each case. In each case, you see pi is directly proportional to, colligative property is directly proportional to number of moles. Okay. So this is called osmotic pressure, everybody. Now listen, what if you apply an external pressure on the solution side, correct? Just to overpower the osmotic pressure. Suppose on this side there is a pressure P naught, this side it is pressure PS. By using some hydraulics here, you apply more pressure here, which will overpower this pressure P naught. In such case, what would happen? This time the solvent particles from the solution will start moving towards the pure solvent form. This side will be the movement. And this movement is called as reverse osmosis. Okay. And this is the phenomena which we use in R water filters, correct, where RO is there, which means where we use electricity and generate that extra pressure which can push the solution towards the pure solvent form. Got it? So this way we will be able to uh, stop all the unwanted solute particles, correct, which are the impurities. So that's how the reverse osmosis works, everybody. Understand these two terms here. Understand this term here, that is tonicity. Tonicity is explaining the type of solution we are dealing with. For instance, if you are comparing two solutions, correct? Two solutions only, and in which one solution, right? One solution has higher osmotic pressure compared to the other solution. Then the one solution which has high osmotic pressure, we call it as hypertonic solutions. These are called hypertonic solutions. And solutions which has lower lower osmotic pressure, they are called as hypotonic solutions. Got it? So that's why if you notice that in medical terms also, right? If you see solutions which are very thick, correct, they are usually written as hypertonic, and the solutions which are very light and they have very less quantity of solute, we call them as hypotonic solutions. Got it? So hypertonic means high osmotic pressure, hypotonic means low osmotic pressure. But if you have two solutions compared of two different solutes, by the way, let's say this is forming due to urea, this is forming due to glucose, but both their osmotic pressures are equal. In that case, we say these two solutions are isotonic solutions. These two are called isotonic solutions. Okay. And now see, two solutions when added, osmotic pressure will also get added, which means because it only depends upon number of particles and doesn't depend upon what type of particles it is. So it's always easier to add them and get the final osmotic pressure. So if you have one osmotic pressure pi 1 is equal to C1 RT, and this is pi 2 is equal to C2 RT, then pi 3 will be equal to C1 plus C2 RT. Okay, clear everybody? This is how we can add both of them. Okay, considering their concentrations, I mean the volume terms are similar here, so that's how we can get it. Okay, clear? Or in case, imagine if the concept, if the volume is changing accordingly, so you will use the volume term accordingly and figure out what is the pi 3. Got it? So I guess these points are clear, everybody. Now let me quickly brief you what we discussed, okay, from colligative properties. From colligative properties, we noticed one thing, that RLVP, relative lowering of vapor pressure, which is by definition delta P by P naught, is equal to mole fraction of solute, which is equal to number of moles of A by number of moles of A plus number of moles of B. Or sorry, this I took it as B here, number of moles of B. Similarly, elevation in boiling point, we learned this as delta TB is equal to KB into M. M is number of moles of B upon weight of solvent, sorry, molar mass of B into, no, weight of solvent in kgs. Okay. Depression in freezing point, that is delta TF, which is equal to KF into number of moles of B by weight of solvent in kgs. Lastly, osmotic pressure, which is pi equal to number of moles of B by V into RT. So notice one thing here. They all are directly related to number of particles that you are adding. So B is a solute particle here. So if B is solute, you can see all of these are directly proportional. So this is the whole point of identifying these four parameters. Got it? Now coming to the real scenarios now. See what happens here is, because they only dependent on number of particles and not on their identity. It doesn't matter how the particle size is. It doesn't matter whether it is bigger size, smaller size, whether they are salt or sugar, their nature. It is independent of all of these terms, isn't it? So therefore, now it becomes very important and crucial to figure out that while you're taking an experimental data, will there be any mismatch between the experimentally identified and theoretically solved pressures or theoretically solved qualitative properties? Now, there is certain abnormality which you will observe. See this abnormality here. Okay. What is the abnormality? The first thing is if the solute is an electrolyte, that means like something like a salt. So by chance, if you are adding a salt here, salt when you add it to water, it will become Na plus and Cl minus. So now you are reading this as 1 mole of particle added, correct? आपको तो ऐसे लग रहा है कि हमने 1 mole of particle add किया है. But once it goes into the aqueous solution, it has become actually 2 moles. So whatever calculation you are doing with respect to 1 mole, which is theoretical, that will not match with the practical values, because practically you'll always see higher values. Why? Because you will see there are 2 moles which are operating in this. So that's why the dissociation or association of an electrolyte becomes important here. Got it? Hence, to account for this change, we need to do some correction in our formula. That correction is done by something called Van 't Hoff factor. Okay, this is done by something called Van 't Hoff factor. Van 't Hoff factor is I. Check. Delta P by P naught is equal to mole fraction of solute, correct? And we write this as number of moles of solute by solute plus solvent. Okay. Now notice number of moles of solute here, where it is there, you just have to multiply that with I. You just have to multiply with the term I. Got it? I is the Van 't Hoff factor here. Got it? Clear? Now that will correct it and make sure now the theoretical value and the practical value matches. Okay. So how do we define this Van 't Hoff factor? It is defined as abnormal colligative property upon normal colligative property, or colligative property actual amount by colligative property theoretical amount. Now, how do we calculate that in terms of various terms? Check it out. In case if there is any dissociation happening, everyone, okay, imagine there is a dissociation happening and I took 1 mole of electrolyte. So let's say 1 mole of electrolyte, and this electrolyte is converting into n moles of some new ion or something. So that means it is getting dissociated. So we can say out of this 1 mole, after some time, let's say some alpha amount has been dissociated. So then this will become n alpha, everybody. So now the total number of moles are actually 1 plus n alpha minus alpha. As per your theoretical calculation, you will take the number of moles as 1. But practically how much we should take? This much. So that means this is the actual colligative property. This is the theoretical colligative property. So therefore, I will be equal to number of moles, which is after dissociation, correct? And number of moles before dissociation, which is equal to 1 plus n alpha minus alpha divided by 1. Okay. So from here, I can say alpha is equal to I minus 1 by n minus 1. So this is the way you can calculate the degree of dissociation also. That how much amount of degree of dissociation of a particular electrolyte has been observed. We can use colligative property and calculate that. Okay. Now notice, sometimes instead of directly giving the information of number of moles, molar mass information is given. That is, what we are trying to do is n actual by n theoretical, correct? This is what we are trying to figure out, I factor. N means weight actual by molar mass actual by weight theoretical and molar mass theoretical. You know that weights will be same because weight does not change. Conservation of mass. So what is changing now? M theoretical by M actual. So remember that colligative property, correct, is inversely proportional to molecular weight of the solute, everybody. Okay. So if you are taking the ratio of the colligative property, which means you should take the reverse ratio of the molar masses. Okay, clear? So if the molar mass theoretically that will be known to you, and actual, which means mixed, molar mass of a mixture. So molar mass of a mixture, if you know that, theoretical by mixture will give you I factor. So for dissociation cases, cases, I value has to be always greater than 1. Okay, clear? Here I have written it. Clear? Now notice for association. For association cases, let us assume that A is in equilibrium with 1 by NB, which means I'm having A moles of electrolytes that is converting into 1 by NB moles of electrolytes. So initially, if you have 1 and 0, now if you have 1 minus alpha, and this will become alpha by N. So this time the total number of moles will be 1 plus alpha by N minus alpha. Okay. So I factor this time will be 1 plus alpha by N minus alpha by 1. Okay. So that is equal to 1 plus alpha into 1 minus N minus 1. So this has to be less than 1, because this value will come out to be negative. So this has to be less than 1. Got it? So you can see alpha value can be calculated as I minus 1 by I minus 1 by 1 minus N minus 1. Clear? So this will be the value for alpha. Okay. And because numerator is negative, denominator is also negative, overall alpha will be positive. That gives you how much is the degree of association. So alpha is termed as degree of association. So if you account for that, you will see for dissociation it will be greater than 1. For association, I is less than 1. For non-electrolytes, I is equal to 1. So when I is equal to 1, theoretical value, practical value always comes out to be same. I hope this part is clear, everybody, right? So this is how you can introduce the Van 't Hoff factor and try to get the actual value or actual answer, how much should be the colligative property. Let me show you through some examples here. So first example, 0.1 molar solution of KNO3 as osmotic pressure of 4.5 atm at 27 degrees. Calculate the alpha of the salt added to the solution. So if it is osmotic pressure, general formula is I is equal to CRT. But now in the C part, you have number of moles. So there you have to multiply that with I. Okay, now this will become ICRT. So therefore it has to be 4.5 is equal to I into concentration is 0.1 into 0.0821 into 300, correct? So you just need to calculate the value of I here. So I will be equal to 4.5 divided by 0.1 into 0.0821 into 300. Okay. Now, you know that I value can be, because our objective is to calculate alpha, I value can be written as 1 plus alpha into n minus 1. Now, why did I write that? See, KNO3, when it dissociates, it will convert into K plus NO3 minus. So, which means 1 minus alpha here should be alpha and alpha. So, this will be 1 plus alpha. So, n value is basically 2 here. So, therefore, I can simply write it as 1 plus alpha. So, I is equal to 1 plus alpha. So, now if I calculate this, alpha value is equal to this entire thing, 4.5 by the 0.1 will become 30, and this will become 0.821 into 3, that minus 1 is equal to alpha. So this is coming as 0.85. So percentage dissociation of KNO3 is 85 percentage. So it is 85% dissociated, hence it is showing the osmotic pressure of 4.5 atm. All of this is clear, everybody? Right. Now, please try this other question quickly. Very similar lines. Do that. See, the osmotic pressure, uh, we need to calculate the osmotic pressure 0.1 normal solution of BaCl2. You know that the valency factor for BaCl2 is 2. Okay. Valency factor for that is 2. Clear? Right. So if that is 2 here, so we can say that molarity is equal to normality by valency factor. So which is equal to 0.1 by 2. Hence, and Van't Hoff factor, I notice this one, BaCl2, if it dissociates, it will become Ba2 plus 2 Cl minus. So that makes it 1 minus alpha, and 2 alpha, that makes it 1 plus 2 alpha. That is your Van't Hoff factor I, which is equal to 1 plus 2 times of 0.8. So we are getting Van't Hoff factor as 2.6. Correct? So substitute that value. So pi is equal to I into CRT. So I is equal to 2.6. Concentration is 0.1 by 2 into 0.0821 into temperature. Temperature is 300. Okay. Solving this, I am getting this as 3.2 atm. Everybody clear? Any doubt here? Right. Now go to this example 3 and try it out. So, let me show this. Now it shows that calculate the alpha of Ba. Okay. Molecular weight of Ba is given as 56. Correct. So that is the theoretical value. So we need to figure out the molar mass of the uh, experimental value, or we can say that as the mixture value. Okay. Now you notice that delta P by P, right, P naught, that will be equal to mole fraction of the solute. Correct. So mole fraction of the solute can be written as number of moles of solute by number of moles of solute plus number of moles of solvent. For these kind of examples, we can always ignore the number of moles of the solute here. So number of moles of solute by number of moles of solvent, which is equal to weight of solute into molar mass of the solvent upon molar mass of the solute into weight of the solvent. Okay, correct. So just substitute these values and see what are the terms which have been given. So this is given as 760 and 751. 760 and yeah, because at 100 degrees, you know that, the vapor pressure for a pure water is supposed to be 760. So 760 by 751 divided by 751. Clear? Uh, Actually, you can do both 760 also here. Then you don't ignore it. In such case, don't ignore it. If you don't want to do this and just ignore this value, in such case, you do it with 751. So that makes your calculation easy and without approximation. So now you notice that Ws into molar mass of the solvent upon molar mass of the solute into weight of the solvent. Now this is coming out to be 9 by 751. That is equal to weight of the solute given is 2 grams into molar mass of the solvent given is this is water, right? Yeah, water. So 18 divided by molar mass of the solvent, which is given as 58 grams, sorry, 56. That into here, sorry, there is some dissociation, so that's what we need to calculate. So molar mass of the solvent, solute mixture into weight of the solvent. Weight of the solvent is 100 grams. Correct. So from here we need to calculate what is the molar mass of the solute, right? Experimentally. Okay. Or actually how much is the molar mass of the solute? Correct. So this calculation, what I did is coming out to be 30.04 gram per mole. Okay. This is the molar mass, everybody. 30.04. Now, Van Tau factor, we know that M theoretical upon M, right? Actual, correct? And theoretically, we are getting this as 56, and actually, we got this as 30.04, correct? And this will be equal to, because it is a salt like Ba will ionize into B plus A minus. So I can write this as 1 minus alpha, alpha, and alpha. So Van Tau factor will be 1 plus alpha. So this can be written as 1 plus alpha. So alpha is equal to 56 by 30.04 minus 1. Okay. So this is coming out to be 0.86. So the percentage dissociation is equal to 86 percentage. Okay. So please do check quickly. If there is any problem, if you have any doubt, you can ask me. Right, everybody, look at this question. Let me explain as well. So 1 gram of monobasic acid is, used here. So you can see 100 grams of water lowers the freezing point by this much. 0.2 grams of same acid requires this much amount of alkali. Calculate the degree of dissociation. Okay. So what we can do, we use first the freezing point data, try to figure out the Van Tau factor, I mean, at least the molar mass factor from here. So we can see we are getting this as 0.168, which is the delta TF, which is equal to 1 gram into 1000 divided by, molar mass actual into 100, correct? That into 1.86, which is a Kf factor. So from here, molar mass actually how much it has, we can calculate that. So that is 10 into 1.86 upon 0.168. Okay. So this value is coming out to be approximately 110.78. So this is the molar mass actual, which is gram per mole. Okay. Next thing what's happening here is, this is an acid which we are reacting with a base. Okay. So therefore you can see HX acid plus NaOH, correct? That will give us NaX plus H2O. Got it? So now we can say that equivalence of HX must be equal to equivalence of NaOH. Correct? Which means at equilibrium, at neutralization. At neutralization, this is what you will get. Okay. So in that is the case, I can write this as N1V1 is equal to N2V2. Correct? Or since the valency factor is 1, I can also write it as M1V1 is equal to M2V2. So now let's calculate, number of moles of the acid given here. How much it is given? See, 0.2 grams of acid is being required. So number of moles of acid given here is 0.2 grams divided by its molar mass. These are the number of moles used. So this is molar mass of the solute here. So that clear. And number of moles of, this is for acid, and see number of moles of base will be equal to 15.1 ml into normality is 1 by 10. Normality and molarity is same for this case. So these are the number of milli equivalents. Millimoles or milli equivalents, that divided by 1000 will give us number of moles of the base. Now equate these two. So 0.2 by m is equal to 15.1 divided by 10 into 1000 here, correct? So from here, if I take M, which is equal to 2000, 2000 divided by 15.1, correct? Which approximately coming out to be 132.45 gram per mole. This is the value of the molar mass. So from here I can calculate Van 't Hoff factor. So this is the theoretical molar mass, and the actual molar mass what we are getting is 110.78. So therefore M theoretical upon M actual, if you do that, you will get this as 132.45 upon 110.78. Yeah. So from here we can get the Van 't Hoff factor. And because it is a monobasic acid like that, so we can say an acid HX can dissociate as H plus and X minus. So X minus here. So I can write it as 1 minus alpha, alpha, and alpha I will be equal to 1 plus alpha. Hence, I can say 1 plus alpha into n minus 1, which is the value of I, that is equal to 132.45 upon 110.78. Hence, alpha value is coming out to be 0.196 or approximately 0.2. So percentage dissociation is equal to 20 percentage. Okay, so please check this out quickly. All good? Right. I hope all of you got that. You made a note? Right, everyone. Let's look into this question now. We have COCl3 dot X NH3. This is the complex given. Got it? So first you got to understand, suppose if X is equal to 3, what will be the case? The complex would be like this: 3 and 3, and that's it. If X is equal to 4, it will be CO NH3, 4 Cl2, and 1 Cl will be outside. If X is equal to 5, cobalt NH3, 5 Cl will be inside, 2 Cl2 should be outside. X is equal to 6, it should be cobalt NH3, 6, and all Cl should be outside. So from here I can say one thing, everybody. So for this case, because there is only one complex form which is neutral, I factor is 1. Okay, nothing is dissociated here. While here, if it get dissociated, then 2 ions will be there. So I factor is 2. While on the other hand, for this one, I factor is 3. And here, because after dissociation, you'll get 4 ions. So therefore, I factor is 4. So now you need to check out which value you are getting. What is the I value you are getting, so that you can correlate with the X value. Okay. So therefore, so now check it out, what we can do. Alpha TF is equal to, okay, Kf into molality into I, correct? So which is equal to 1.86 into molality. Molality is 0.1 multiplied by Van't Hoff factor I. Okay. Okay. So in that case, what will be the Van't Hoff factor I here? So check out. I will be equal to 0.558, which is given as delta T. Hmm. That divided by Kf, which is 1.86 into 0.1. So this value after calculate, I'm getting it as 2 beta. If it is 2, then correlate with which particular case it is. This is the case, right? For this case, what should be the x value here? X value should be 4.
Sir, that division gives 3.
I mean 3, 0.0. Sorry, higher, sorry. Yeah, sorry. In that case, it is 3, right? This is coming out to be 3. So x value should be 5, correct? You're right. Hmm. Clear? Everyone, please check. Okay, do this next question. Check it out, guys. What is the amount of ice that will be separated out on cooling of solution containing 50 grams of ethylene glycol in 200 grams of water? See, it's like this. Let's say water is sorry, an aqueous solution is freezing at minus 2 degrees. Okay, imagine. But if you keep on going till minus 10 degrees or minus 11 degrees, that means out of that solution, slowly lot of part will start converting into ice. Now it is that particular situation. When the temperature is 9.3, then out of this 200, how much amount has been the ice formation? So after losing out that ice, then the remaining amount will be as the solution. And I told you this specifically, the number of moles of solute never get converted into ice. So they will remain in solution only. So number of moles of solute will never change. Okay. Take that important logic here in the question. Okay. So check this out. So we know that delta T F is given as 9.3. Okay. And if I put that into the formula, that is equal to Kf into M into I. Sorry, it is ethylene glycol, so it will not ionize. So only Kf into M. So that is equal to Kf into number of moles of solute upon weight of the solvent in kgs or grams into 1000. This is how I can write. Correct? Now, what I can say, out of this weight of solvent, some amount of uh, ice has been formed. Correct? So we'll do one thing. Let's calculate what is the weight of the solvent in grams, which is in liquid state now, because this concentration calculation is as per the liquid state now. So that will be equal to Kf into N into 1000 divided by delta Tf. So therefore, weight of solvent in grams will be equal to Kf is 1.86 into number of moles. So number of moles will be weight by molar mass. So 50 divided by molar mass. Molar mass of ethylene glycol is coming out to be 62. So that 62 into delta Tf is 9.3 into 1000. Got it? So this will be the weight of the solvent, everybody. Okay. So on my calculation, I think it is coming out as 161.3 grams. This is the weight of the solvent. So how much is the weight that has formed into ice? Therefore, weight of water, okay, converted into ice, converted into ice will be equal to 200 minus 161.3. Got it? So this is coming out to be 38.6 grams, approximately 7 grams. Please check if you got this, everyone. Any doubt here? Right, check this out, everybody. A solution of 1.21 grams of solute in 26.7 grams of acetone boils at this amount. So delta TF is what we need to calculate that. So therefore, let me directly write that value here. Delta TB, correct. So that is equal to KB into molality. Acetone does not ionize. If there was anything about ionization, that values will be given to you. Okay. Sorry. I meant to say the solute. Solute hasn't been ionized. If there is something, it will be given to you. Anyway, so KB value here, how do we write down that? KB will be equal to delta TB. Sorry, this let me write down into number of moles into 1000 into weight of solvent in grams. So KB value will be equal to this into weight of solvent divided by number of moles into 1000. So that is equal to delta TB into weight of solvent. Weight of solvent is 26.7. That divided by number of moles, which is 1.21, divided by molar mass 152 into 1000. Okay. So KB is coming out to be delta TB is how much? 329.5, correct? So 0.5 into 26.7 into 152 upon 1.21 into 1000. Got it? So this is the KB value. KB value, I'm getting it as 1.67. Tanish, please check if you are close by with this value. Yeah. So now KB value will be equal to RTB square into molar mass of the solvent, that divided by 1000 times of delta H of vaporization, correct? So from here, I can write delta H of vaporization is equal to R. Now it depends upon what you are taking. I am first writing it in kilojoules. For kilojoules, the value of R I'm taking is approximately 2. Maybe if I take 1.98, that's where I'll get to the closest answer of what you got. So that into this value is 329.3 whole square into molar mass of solvent, which is acetone, is 58 upon 1000 into KB. KB value is 1.67. Okay. So you multiply all of that. This is coming approximately 7.5 kilocalories, which is close to 32 kilojoules. Okay. Please check. Everyone, please do check. What is the ratio of the weight of methanol and glycerol, which would require to lower the freezing point of 1000 grams of water by 10 degrees? Okay. So which means delta TF has to be 10 degrees, correct? So if this is 10, which is equal to Kf into weight of CH3OH, okay, so that divided by molar mass of CH3OH, correct? So that into weight of solvent. So weight of solvent is the same thing here. It's not changing. Similarly, 10 is equal to Kf into weight of glycerol divided by molar mass. Okay. Uh, Molar mass of glycerol is 92. Correct. So I'll just write down here molar mass of glycerol, that into weight of solvent. Yeah. Now you can see both should be equal. So I can take the ratio W1 by W2 into m2 by m1, that should be equal to 1. Okay, so which means weight ratio should be W1 by W2 is equal to m1 by m2, correct? Which is equal to 32, which is the molar mass of CH3OH, and 92, which is the molar mass of glycerol, which is 8 by 23, correct? So 8 by 23 is approximately 0.3435. That's it. That is the percent weight ratio. Okay. Everybody look into it.